Okay, what I would like to do is cover sections 1.1 and 1.2 in the course, since we can't meet in person on Tuesday. So again, you should have your notes that I posted in Canvas for you. And I'm sorry you can't really see this that well, but again, I'm just following along with the notes, so you should too. Okay, so section 1.1, we're discussing sets. And it says you can think of a set as a collection of objects called elements or members. I've underlined elements or members, meaning that's the terms I'm defining. The order of elements in the set does not matter. Duplication does not matter either. So my first example, I have the set with the elements 1, 2, 3, the set with the elements 2, 1, 3, and the set with the elements 2, 2, 3, 1. But all three of these sets are exactly the same thing, because 1, 2, 3, and 2, 1, 3, they're the exact same elements, just in a different order. That doesn't affect anything. And 2, 1, 3 compared to 2, 2, 3, 1, well, 2, 2 in a set, duplication doesn't matter. Nobody would ever write this set as 2, 2, 3, 1. They would just write it with a single 2. So all three of these sets are saying the same thing. Again, we denote sets by braces. And the elements are the items that are listed inside the braces. Okay, so throughout the course, we're going to be using certain notation to indicate sets of numbers. Some of these you've already seen. For example, the double R, again, look in the notes, you can see it pretty well. That's the set of all real numbers. You should know what the real numbers are. The double C is the complex numbers. Remember, those are numbers of the form A plus BI, where I is the square root of -1, and A and B are real numbers. So, for example, 2 plus 3i is a complex number. The rational numbers, that's your integers divided by a non-zero integer, 2/3, 5/7, -8/51. Okay, those are your rationals. Integers are 1, 2, 3, 4, 5, ... 0, -1, -2, -3, ... So natural numbers, or your counting numbers, 1, 2, 3, 4, they're positive integers. And this book is using the double I for integers. That is not a standard notation. Just be aware, you may look in other books and they wouldn't even mention this I. The other ones are common, but the I is not. Now, something we can do to indicate other special sets related to these, suppose we didn't want all the real numbers. Well, if you put a plus as a superscript, that's R plus, that's your positive real numbers. R minus are your negative real numbers. R star are all real numbers except for 0. The star just says throughout 0. And R non-negative, so that's throwing out the negatives and, well, wait, non-negative, it's just throwing out the negatives. So 0 would be in this set. So this would, R non-neg is not the same as R plus. R plus are positives. R non-neg is positives with 0. Now, and all these little superscripts, you can put on these other sets as well. You could do Q plus. You could do Z plus, you could do Q star, non-zero rational numbers. Okay, so you can mix and match. However, C plus doesn't make any sense, right? Complex numbers, there's no positive or negative. Is 2 minus 3i a positive complex number or a negative complex number? That doesn't make any sense, okay? Same for C non-neg, that doesn't make any sense. Now, C star does make sense, right? Star just means throughout 0. So C star would be all complex numbers except 0. So just keep in mind, something complex is the only one that's an issue with the plus and the minus and the non-neg. Okay, now how do we indicate whether an item is an element in a set or not? We say X is an element of A or X is not an element of A. So a lot of times in mathematics, whatever symbol you have to do the not, you put a line through it. So you have X is an element of A, X is not an element of A. Now, another way to write sets, notice here I just listed elements. You can just tell me that has 1, 2, 3, right? 1, 2, 3, 1, 2, 3. But if it's, these are, well, infinite sets, or you can't just list every complex number. You can't do that. So we'd like to have another way of describing sets besides just listing elements. And so this is the set builder notation. So the way you read this, it's the set of all X in the set S such that, or with the property that, P of X. Okay, so there's two restrictions here. First, X has to be in whatever set this is, and then it also has to have this property, P of X, whatever that is. Okay, so we'll do an example of that in a second. So the next examples say fill in the blank here with either is an element of or is not an element of. So the first one says 5 blank the set 1, 3, 5, 7. Well, let's look at the set 1, 3, 5, 7. What are the elements in that set? 1, 3, 5, 7. Is 5 in the set? There it is, yes. So the answer to this one is element of. 5 is an element of that set. Okay, now let's look at the next example. Is 2 an element or not of the set with 3 cat and the set with 2? What are the elements in this set? 3, cat, and the set with 2. Now, clearly, 3 and cat don't have anything to do with the 2 over here. So the question is 2 the same thing as the set with 2? No, they're not. The set with 2 is a set with something in it. 2 is just a real number. Okay, so 2 is not an element of this set. Because 2 is not in the list. The set with 2 is, but the set with 2 is not the same as 2. Okay, now notice this set here on the next example, it's in the set builder notation. It's the set of all x and q, so rational numbers, such that x is between minus pi and pi. So the only way negative a half can be in this set with the set builder notation is if negative a half satisfies both of these properties. Well, negative a half is a rational number. It's an integer over a non-zero integer. And negative half is between minus pi and pi. So negative half satisfies both of those conditions, so we do have element of. Now, just for contrast, what if on the other hand, my set here had been x in z such that minus pi is less than x is less than pi? If this had been x in z, I wouldn't even have to check the p of x condition here, because negative a half is not an integer, it's a rational number. So if this had been z, negative a half would not have been an element. Then lastly, we have the set with 6. Is that an element of the set with 2, 4, 6, 8? Well, what are the elements in the set on the right? 2, 4, 6, and 8. Obviously, the 2, 4, and the 8 don't have anything to do with anything. So 6 is an element of this set. This is the set with 6. It's the same argument up here the other way around. The set with 6 is not in the list, so this is not an element of. Now, if I had braces around the 6 here, and that would have been the set with 6, the set with 6 would have been in the set. Likewise here, if I put braces around this 2, 2 would have been an element, the set with 2 would have been an element of this set. Okay, then the last example on the page says, here's the set, it's T is the set of all x and z, those are integers, where x is between minus 5.3 and pi. They say rewrite the set by listing the elements in the set. Okay, so they just wanted to list. So it's only integers, and what integers are between negative 4.3 and pi? Well, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, and 3. Normally, if it's a small set, you just write out the elements like we did here. If it's a larger set, then you want to use the set builder notation. Again, if this had been, for example, x's real numbers, you couldn't just write the list because there's an infinite number of real numbers there. Okay, so that's the first page. Okay, let's practice more with the set builder notation. So the next example, notice I have negative 2, I have the number negative 2, I have number 2 written in parentheses there. That means I copied the problem out of the book. Okay, so that whenever I do that, it's coming from the homework exercise. If I don't have a number next to it, that means I made the problem up. Okay, so this problem says, we have this set S, which is negative 2, negative 1, 0, 1, 2, 3. Okay. So we have a set with 1, 2, 3, 4, 5, 6 elements in it. Okay. It says describe each of the following sets as x and s such that p of x, where p of x is some condition. So they want you to, this problem is backwards from the one we just did. They gave a set builder notation and we made a list. Here they're giving you a list and they want set builder notation. Right? So the first, let me just write these down. So the first one is the set A is 1, 2, 3. The next one is B. 0, 1, 2, 3. The set C is minus 2, minus 1. And the set D is negative 2, 2, 3. Usually with sets, we identify them with capital letters. That's the standard thing. So you would almost never call a set little a. Okay. And notice here on this example, in the instructions, they put x and s colon. I wrote my set builder notation with a vertical line. Colon is a perfectly acceptable notation. The book is usually using the colon. I like the vertical line, so I will probably stick to the vertical line when I do examples. Okay, so every single one of these, they want you to write in this form. X in S such that. 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 Okay, so all we have to do, and every single one of these elements that's listed in all these sets A, B, C, D is in the set S, so that's no problem. So they want us to put a property over here such that when you restrict S to this property, you get these. So what's something, and they don't care, anything you want as long as it makes sense. How about for this first one, 1, 2, 3, it's the number, they're ranged from smallest to largest, it's the 3 largest numbers over there. So we could say X and Z is such that X is bigger than or equal to 1, couldn't we? So if you take all the elements of S, which ones are bigger than or equal to 1? 1, 2, 3. That's what I'm trying to describe. So that's a possibility. The next one is 0, 1, 2, 3. We could play the same game. 0, 1, 2, 3 are the largest 4 elements. So we could say X bigger than or equal to 0 here. So that works. Now negative 2, negative 2, negative 1, those are the smallest ones. So we could just say, for example, X is less than or equal to negative 1, do the opposite that we did there. But just to be different, I came up with this. What if we said X plus 2 times X plus 1 is 0? What if I put that condition on? Well, what X's satisfy this equation? Only negative 2 and negative 1. So there's multiple possibilities here. Now what about negative 2, 2, and 3? So negative 2 is the smallest value, 2 and 3 are the largest. And again, there's many possibilities. You could do the same thing I did here and make an equation where those are the solutions. You could do that. I came up with the following. Absolute value of X is bigger than or equal to 2. Notice 2 and 3, they're an S with absolute value at least 2. And negative 2 has an absolute value of at least 2. So there's many possibilities here. I was trying to give a variety. So absolute value inequality, solutions to an equation, or just inequalities. Okay. Okay, the next definition says the empty set or the null set or the void set. I usually just say empty set or null set. It's the set with no elements in it. Okay. We've had examples of a set with 1 element. Here we had a set with 6 elements. We did ones a little while ago with 3 elements. But what about a set with no elements in it? There's nothing in it. So that's called the empty set or the null set, and you write it either as braces with nothing in it, that means empty set, or you do a 0 with a slash in it, that's the empty set. So those are saying the same thing. Now be careful, that is not the same as the set with the empty set inside, because this is a set with something in it. So this set has 1 element in it, so that's not the same as the empty set, be careful. So for those of you in computer science that like writing your zeros with a hash through them, be careful. I may confuse that with empty set. Okay, the next example says, consider the following set, X in the real numbers, so all real numbers here, with the property that the absolute value of X is negative 4. Okay, so let's think, which real numbers have an absolute value of negative 4? Well, whenever you take the absolute value of a real number, you always get a number that's at least 0. So there is no real number for which the absolute value is negative 4. No real numbers satisfy this property. So this is the same thing as the empty set. That's just a fancy way of saying empty set. Okay. The last definition in this section says, if S is a set, if you put vertical bars around it, now be careful. Don't read this as absolute value. You take the absolute value of a number. This is a set. Big S stands for a set here. So you read this as the cardinality of S. You have to get it from context. The cardinality of S, that is the number of elements in the set. So when you see vertical bars around a set, that's asking for the cardinality, how many elements are in the set. If the cardinality of S is n for some non-negative integer, we say the set's finite. Otherwise, we say the set is infinite. Okay, so we can have finite sets like 1, 2, 3. The empty set is a finite set. There's 0 elements in it. But the real numbers is an infinite set. The complex numbers is an infinite set. So as an example, I think I just said this. It says, what's the cardinality of the empty set? How many elements are in the empty set? None. Then it says, what's the cardinality of the set with 2? The set with 2, and the set with 2. So the question is, how many elements are in this set? Well, what are the elements in this set? So there's my set brackets. So let's look inside. I have a 2, I have a set with 2, and the set with 2. Hopefully, based upon our discussion before, you realize 2 and the set with 2 are not the same thing. The set with 2 and the set with 2 are not the same thing. These are 3 different things in the set. So the cardinality of this set is 3. And then lastly, it says, what's the cardinality of the complex numbers? The complex numbers is an infinite number of things in that set. That answer is infinity. Okay, so that's just a lot of definitions. Make sure you know your definitions. So let's move on to section 1.2. And there's really two definitions in here to talk about. And I know some of this you've seen before, and that's fine. So section 1.2 is on subsets. Now, what's the definition of a subset? So what does it mean for A to be a subset of B? It's exactly what you think it is. That means everything in A, every element of A is an element of B. So in words you can write, if X is in A, if X is an element of A, then X is an element of B. That's the actual word definition of A is a subset of B. If X is an element of A, then X is an element of B. So if you're trying to show A is a subset of B, this is what you want to show. Okay, now what does it mean for A to not be a subset of B? What does that mean? That means there exists an X in A with X not in B. Right? Because if everything in A was in B, you would have a subset. So if A is not a subset, that means there's an element of A. It may only be one. It could be more than one. There's something in A that's not in B. Okay. And, proper. Now, what is it? In mathematics, whenever you hear have the adjective proper subset, or proper anything, that proper just means it's not the whole thing. Okay? So if A is a proper subset of B, that means A is a subset of B, but A is not the whole thing. A is not all of B. That's all proper means. Okay? Now keep in mind, different books use different notation. In this book, they're writing A is a subset of B this way, with the subset symbol and the equal. That means A is contained in B, and A can also equal B. This book is using proper subset without the little equal to it. It's just like when you did real numbers. If you say X is greater, let me do less than. If X is less than or equal to 5, X is smaller than 5, but X could also be 5. And if you take off the line here, X strictly less than 5, X can't be 5 anymore. Okay, that's the notation, similar notation they're using here with subsets. So here, everything in A is in B, but A is not all of B. A is proper. Now you can also, and I'm perfectly fine if you use this notation, other books don't do this. Sometimes for proper, they leave the line there, but then they put a little hash mark through the line. So A is a subset of B, but not all of B. So other books may use this, and I may actually accidentally use this because I'm used to this as well. Okay, so just realize there's a difference between subset and proper subset. Subset could be the whole thing, proper cannot be the whole thing. Okay, now what does it mean for two sets to be equal? Whenever you learn about anything in math, you always want to know what does it mean for two things to be equal. So what do we mean for two sets A and B to be equal to one another? Okay, the definition is A is a subset of B and B is a subset of A. Notice what they've done here. In math, whenever you learn something new, you want to write it in terms of things you already know. We just talked about subsets here, and notice that's what's used here. So two sets are equal if each one is a subset of the other. So if A is a subset of B, everything in A is in B, and if B is a subset of A, everything in B is back in A. So your sets are equal. So this is the definition. Right? You have to know your definitions. Okay, let's do some examples. I'm not going to write this down. We'll just talk about it. It says, let A be the set 2, 4, 6, B is the set 4, 6, 8, and C is the set 2, 4, 6, 8. The first question says, is A a subset of B? Notice it's not questioning proper, just says A is a subset of B. Well, what does it mean for A to be a subset of B? Every element of A is an element of B. 4 is an A and in B, 6 is an A and in B, 2 is an A but not in B. So notice there is something in A that's not in B, so A is not a subset of B. Now what about A as a subset of C? It looks like every element of A, 2, 4, 6, is also in C, 2, 4, 6, 8. So A is a subset of C. B subset of C, same thing. Every element of B, 4, 6, 8, is also in C, 2, 4, 6, 8. So B is a subset of C. Okay, now the next example says A is a proper subset of C. So there's two things to check. Is A subset of C? Yes, we just said that earlier. And now for proper, A is a subset of C. Is A all of C? No, it is not, because A is 2, 4, 6, C is 2, 4, 6, 8. So A is not the whole of C, and so A is a proper subset of C, so that's a yes. And then the last part there is B a proper subset of B. Every set's going to be a subset of itself, because everything in this set is going to be an element of itself, but that's proper. So how could B be a proper subset of B? There has to be something in big B that's not in the small, the subset B, and that can't happen, so that's a no. Okay, now what about part B here? Is 4 a subset of A? Now I'm trying to be tricky here, and the book does this too. Right? What was the definition of subset? A and B are sets. And is every element of A an element of B? Notice 4 there is not a set, it's just a number. That question makes no sense, so the answer is no. Now look at the next one. Is the set with 6, that is a set, is that a subset of C? Now what does the definition say? Let me write that down. So the set with 6, is that a subset of C? And remember, C is 2, 4, 6, 8. Right? Now, what does subset mean? Right? Is every element of this set 6 an element of that set? 6. Okay, so when you do subset, you have to look inside, right? What are the elements inside? 6 is here, 6 is here. So the answer is yes. Okay, now I want you to compare this to when we did element of. Okay, okay, that's the next question. There we go. Is the set with 6 an element of C? Now, to be an element, the whole thing, whatever's here, has to be in the list. That's a 6, not a set with 6, so that's no. So please differentiate between element and subset. To be an element of a set, whatever's here, the entire thing has to be in the list. The set with 6 is not in the list, so this is not an element. But for subset, it's everything in the set has to be in the set. So this is a subset. Okay? Okay, so there's more examples down at the bottom. Is the set 7, 1 a subset of the set 4, 1, 8, 7? Okay, to be subset, everything on the left-hand set, in this left-hand set, has to be in the right-hand set. The elements on the left are 7 and 1. They are on the right in the right-hand set, so that is true. Okay, so the B says the set with 8 is an element of the set 1, 8, 9. If you want to, pause the video and think about that for a second, then turn it on and I'll tell you the answer. Okay, so the set with 8, to be an element, that whole thing has to be in the list, and it's not. So that's false. And then the next one changes it up. So the next one changes that from the set with 8 is a subset of the set 1, 8, 9. Okay, so to be a subset, every element inside the set, 8, has to be an element of this set, 8. There it is. So this one is true. And now we're getting more complicated. So the next one says, is the set with 8 an element of the set with 1, the set with 8, and the set with 8, 1? Again, if you want to turn off the video and think for a second before you hear the answer, feel free. Okay, so what does it mean to be an element? This whole thing, that entire element, has to be in the set here. There's a 1, there's a set with 8, there's a set with 8, 1. That right there is that element right there. So this is true. Okay, the next two involve our large sets with our notation. Is Z a subset of R? Just in words you would have learned in middle school, what is this saying? Is every integer a real number? That's all this is asking. Is every integer a real number? Yes. So that's true. The next one says real number, subset of the complex numbers. So is every real number, is every element in here? So is every real number a complex number? And that is yes as well. Now you may not think of it this way, but remember what the complex numbers look like. They're of the form a plus bi, where I is the square root of -1, and a and b are real numbers. Pick your favorite real number, square root of 7. Can't I write square root of 7 as square root of 7 plus 0i? Square root of 7 is square root of 7 plus 0i. Notice this is a plus bi, where a and b are real numbers. So this is an element of the complex number. So every real number you can do this trick, right? A is the same as a plus 0i. So every real number is a complex number. You may not realize that, but it is true. And then the last example there says the set with 2, 3, 4 is a subset of the set 3, 4, 5. So what does it mean for one set to be a subset of another? Is every element of this set an element of this set? Now 3 is here and 4 is here and here. 2 is in this set, 2 is not in this set, so that is false. Okay, so that's just practice with elements and subsets. Okay, now on these next couple of examples, I am getting a little ahead of myself. I mean, the title of the name of this class is a little misleading. It's called Discrete Math, but this is really the introduction to proofwriting for the math majors. And so I am going to do a couple of proofs here, even though we haven't really gotten to proofs yet. I just want you to see where we're headed. So it says fact, the empty set is a subset of every set. Okay, so we're going to prove that. Proof. Right. And then we can use it. We need this fact right now. I think in the book they just say it's true and then they move on and they prove it later in the book. Okay? So what we're going to do here, and again, I'm getting way ahead of myself, we're going to prove this by a method called contradiction. Okay? So every statement's either true or it's false. So let's assume the negative of this is true. Okay? So the empty set is a subset of every set. So what if this weren't true? That means there's a set for which the empty set is not a subset, right? Okay, so let's assume there is a set A for which the empty set is not a subset. In other words, i.e., the empty set is not a subset of A. That's just writing it in symbols. Okay, so assume there is a set big A for which the empty set is not a subset. In other words, the empty set is not a subset of A. So it's the negation of this. Okay, we haven't really gotten to that yet, but right. So if this weren't true, if the empty set were not a subset of every set, there would be a set for where the empty set's not a subset of A. Okay, now we talked about this before when we were doing subset and not a subset. What would this mean, right, if for the empty set to not be a subset of A? Okay, right, so what would that mean? Thus, there exists an element of the empty set that is not an element of A, right? When we had before, A was not a subset of B, that meant there was something in A that's not in B. So if the empty set is not a subset of A, that means there's an element of the empty set that's not an element of A. Okay, so we're just following logically. Assume this isn't true, so there is a set that the empty set's not a subset of. If the empty set's not a subset of A, that means there has to be something in the empty set that's not an element of A. So that's where we are. But what is it? What did we just say? There exists an element of the empty set. That right there, that's a problem, right? Since the empty set has no elements, we have reached a contradiction. So we assume that this statement, we assume the negation of this was true, and we ran into a problem. Which means the negation can't be true, so that means this one must be true. Okay? So just a conclusion, hence, the empty set is a subset of X, big X, for all sets big X. And I'm going to put a little black box at the end to indicate I'm done with my proof. Actually, I was doing a proof, and you indicated proof with a black box or an open box or a diamond, or, you know, different books and different research papers use different things. So there's our proof. So it's not the proof I'm so concerned about right now. I just wanted you to see where we're headed. But I want you to make sure you know the fact. The empty set is a subset of every set. Okay. Now, a nice property of sets, which may be obvious to you, is the transitivity of subsets. Now, transitivity in math, we see that in many, many places. So let me just tell you what, whenever you see transitivity in math, think of it this way. If A is related to B somehow, and B is related to C somehow, transitivity means that A is also related to C. Whatever related means here, okay? So if A is related to B and B is related to C, then A is related to C. If that property is true all the time, you've got transitivity, okay? So the transitivity of subsets, the theorem says, so A, B, and C are sets here. I didn't write that down. But it says if A is a subset of B and B is a subset of C, then A is a subset of C. So what's the is related to? When I said A is related to B, B is related to C. A subset. If A is a subset of B and B is a subset of C, then A is a subset of C. So this is called transitivity of subsets. Okay, so let's do the proof. Again, we're getting ahead of ourselves. Now, I'm going to prove this. The last one we proved by contradiction. We assume the negation of the statement. So we're going to prove this one directly. Whenever you have an if-then statement and you're proving directly, what do? You assume the hypotheses, the if part, and you show, assume that's true, and then you show the then part. So you assume the hypothesis and then you prove the conclusion is true. So I always say, assume the if and show the then. So you assume the hypotheses and then you prove the conclusion. Okay? So that's what it means to do a direct proof. That's where we're going to be starting in this course when we get to proofs, is doing direct proofs. Okay? So let's assume the hypotheses. Assume A is a subset of B and B is a subset of C. Just, right? You don't want to put 1,000 things in your first sentence. Assume A is a subset of B and B is a subset of C. Okay, now we want to show A is a subset of C. Now, how do you show one set is a subset of another? So this is a little scratch work here. This means if X is in A, then X is in C. That's what this means right here. That was the definition of subset. If X is in A, then X is in C. So if I can prove this, I have A as a subset of C. Now, how do you prove an if-then statement? You assume the if part, and then you show the then. So to prove the giant if-then statement, I assume this, and I need to show this. But to show A is a subset of C, that's the definition. Assume X is in A, show X is in C. Okay, so let's assume something, there's an element in A. So let X be in A. And again, anybody, somebody that knows this already, as soon as I put let X be an element of A, they know I'm doing this. You don't really have to write that down. So let X be in A. So I have three facts here. A is a subset of B, B is a subset of A, and I'm letting X be an element of A. So I need to show that X is an element of C and we'll be finished. Well, X is an A and A is a subset of B. Since X is an A and A is a subset of B, what can we conclude? We conclude that X is an element of B, can't we? Because what's the definition of A is a subset of B? If X is in A, then X is in B. We have X is in A, that means X is in B. And now we have X is in B, if we use the same argument, so likewise, this is telling the reader I'm doing the same thing, same idea. Since X is in B, and B is a subset of C, we conclude that X is in C. Okay? We know X is in B, B is a subset of C. By definition of subset, X is also in C. So notice what we did here. We started with X is in A. We got that X is in C. Well, if something is in A and we showed it has to be in C, what does that mean? Thus, A is a subset of C. Which is what we were trying to show. Right? Assume A is a subset of B and B is a subset of C, and I just showed A is a subset of C. Okay? So therefore, I'm going to write the conclusion. Therefore, if A is a subset of B and B is a subset of C, then A is a subset of C. I've just restated the original problem. And there's my little black box to indicate the end of the proof. Again, I'm getting way ahead of myself. If you sort of follow what I did, that's good. We're not at this point where you can do this yet. I just wanted to show you where we're headed again. Okay, the last definition here, and which is why we needed that previous result on the empty sets, a subset of every set, is called the power set of a set. So what we're doing here, we're starting with a set, and we're making a new set from it. Okay? So we're going to start with a set and make a new set from it. So the definition says, given a set A, so here's A, the power set of A, and the notation for that in this book at least, it's a script P with the A. So this is my original set A. This says, what's the power set of that? The definition of the power set of A, it's the set of all subsets. So this is the set of all subsets of A. So we already talked about subsets. So if I give you a set A, you list all the subsets, all possible subsets of it, and make that a set. That's the power set. So just to get a feeling, let's compute these examples here. So the first one I say, let A be the set with just A. So it only has one element in it. Okay, so always label your work. So what is the power set of A? The power set of A is a set. It's the set of all subsets of this set. So what are all the subsets of my set A? Well, we just learned the empty set's a subset of every set. So the empty set's a subset of that set. What else is a subset of this set? The whole thing. And that's it. So these are the only two subsets of my set A. So if A is the set with A, the power set of A is the set with the empty set and the set with A. The next example says, suppose A is just the empty set. So A is the empty set. What's the power set of A? Now remember, the power set is the set of all subsets of A. We learned earlier the empty set's a subset of every set. So it doesn't matter what's here, the empty set's always going to be in the power set of any set, because the empty set's a subset of every set. There are no other subsets of the empty set, so that's it. And then the last one example says, W, X, Y, Z. Let me come over here. Okay, so suppose A is the set W, X, Y, Z. My Z's have a hash mark through them, my 2's do not. That's how you can tell my 2's from my Z. Z says a hash mark. Okay, now what's the power set of A? So the power set of A, it's the set of all subsets of this set. Now you really want to do this with some sort of strategy. So I usually just say, let's take, what are all the subsets with no elements in it? Empty set. What are all the subsets of A with exactly one element? The set with W, the set with X, the set with Y, the set with Z. Now let's list all these subsets with exactly two elements. WX, WY, WZ, that's W with everything. Now let me do X with everything else. X with Y, X with Z, and then YZ. So I have all the sets with no elements, one element, two elements. Now I need all the sets with three elements. Now instead of trying to take all combinations of three things, whenever you're trying to do, there's four elements in the set, I'm trying to do things with three. Instead of trying to find all the things with three, just eliminate one of them. So if I take out the W, I get X, Y, Z. If I take out the X, I get W, Y, Z. If I take out the Y, I get W, X, Z. And if I take out the Z, I get W, X, Y. So that's an easier strategy than trying to do three things at a time. Just take one thing out. And then lastly, I need the subset with four elements, which is W, X, Y, Z. And be careful, it's the set of all of them, so that's a big brace for the whole thing. Okay, so there's a lot there. Okay, so let's look at cardinalities here. Let's compare the number of elements in the set with the number of elements in the power set. Let's make a table here. So cardinality of A and cardinality of the power set of A. Remember, vertical bars mean how many elements are in the set. So when we had the empty set, there were no elements in A, but how many elements were in the power set of A? One. We didn't do two, but when A has one element in it, the power set had two elements in it. And when A had four elements, what did I say before? Sorry. A had 0 elements, A has 1 element. Yeah, we didn't do 2 here. Okay, and we didn't do 3. But here's 4. So suppose A has 4 elements in it. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Now the reason why I'm doing this, because this is coming later, but from this observation, hopefully you'll notice the cardinality of the power set of A. Let me do that again. The cardinality of the power set of A is 2 to the cardinality of A power. Notice, if A has no elements, how much in here? 2 to the 0, which is 1. Notice when we have 1 element in A, it's 2 to the first, which is 2. And when we had 4 elements in A, it's 2 to the 4th, which is 16. Now, the reason why I'm getting, again, we're getting ahead of ourselves here. The reason why I'm mentioning this is because if you have a problem like this, you know how many elements are going to be in the power set before you start, right? So if you know this formula and I give you a set with, if I said, A has VWXYZ, A had 5 elements in it, you know the power sets can have 2 to the 5th or 32. So once you get through, you could say, do I have 32? And then you know you got them all. So that's why I'm mentioning it now, because that'll help you when you're working on problems. You know how many sets are going to be in the power set before you start. And then lastly, I want you to understand the connection here. Okay? Now remember the power set, okay, you have a set A. The power set of A is just another set, right? Here's a set, there's a power set. There's a set, there's the power set. We had a set with a lot of sets in the power set. Okay? So you start with a set A and you get a power set from it. What if I told you, what if I said the set B was an element of the power set of a set A? So B is an element of that. Right? Right? What is that saying the same thing? It's the same as saying what? Right? If B is an element of the power set of A, think of that example I just had. If B is an element, it's in the list somewhere. And everything in the list in the power set of A was what? That meant B was a subset of A, right? Remember, the power set of A is the set of all subsets. So if B is an element of the power set of A, that means B is a subset of A. These are saying the same thing. So keep that in mind as you go through the course. Students get confused about what do things in the power set look like. If B is an element in the power set, that means B was a subset of the original set. Right? Because when we had W, X, Y, Z for A, right? What's a subset of that? For example, WXZ is a subset, right? Every element in here, WXZ, is in there. So this set B is a subset of A. But remember, that was one of the sets in our list in the power set. So that is also an element of the power set. So realize these are saying the same thing.